Good morning, students. Today's video lecture is probably of the most important lecture of this chapter solution in terms of both boards as well as for competitive exams. Topic is want of factor. Before discussing want of factor, come to this term colligative properties. Now, colligative properties are the properties of solutions which depend upon number of solute particles. Remember this, number of solute particles in solution. Okay, again, colligative properties CP are the properties of solution which depend upon number of solute particles. More are the number of solute particles, more will be the value of a particular colligative property. In detail, we will study about colligative properties in next lecture. But today's topic is this, want of factor, which relates with number of solute particles. But want of factor is the ratio of number of solute particles which are actually present in solution to the number of solute particles initially dissolved in the solvent. I can show this with example. Suppose I have 6 pens. 1, 2, 3, 4, 5, 6. Consider each pen as a solute particle. We have 6 solute particles. Suppose when this solute is dissolved in water, some of the solute particles get dissociated. Just like acetic acid, it gets dissociated in water as CH3COO negative and H positive. Means one solute particles get dissociated into 2. In case of this pen, one pen dissociated into 2. So initially number of particles I've taken 6. Suppose 2 pens get dissociated. How many particles I have? 1, 2, 3, 4, 5, 6, 7, 8. Mathematically, consider we have initially pen, consider it as AB. It dissociated as A and B. Let it be A positive, B negative, pen body, pen cap. Initial situation was, we have taken how many pens? 8. 0, 0 before dissociation. Final means when solute particles are dissolved in solution. We have 2. How many left? Complete pens? 8 minus 2. Again, I'm just demonstrating this with the example of pen. Initially, we have, not 8, 6 pens. 6. We have 6 pens. 1, 2, 3, 4, 5, 6. 6 solute particles which are to be dissolved in water. 6. In water, how many particles? Initially, 0, obviously. Alag hai. When these particles mixed in water, some of the particles get dissociated. Let it be 2. Get dissociated. 1, 2. Now I have 2 A positive and 2 B negative. How many complete pairs are left? 1, 2, 3, 4. Okay. So what is the value of want-of factor? I. I is the number of solute particles in solution after dissociation. How many particles we have? 4 complete and 2 plus 2 dissociated. 4 plus 2 plus 2 in the solution divided by initially taken 6 comes out to be 8 upon 6, 4 by 3, approximately 1.33. Got it? Next is degree of dissociation alpha. Now alpha is the ratio of number of particles which actually get dissociated or associated divided by number of particles originally taken. Consider the same example of pens. Alpha is equal to number of particles which get dissociated. How many get dissociated? 2. Originally taken 6. So alpha is 1 upon 3. It's 0.33. I'm repeating. What is the I? I is want-of factor, which is the ratio of number of particles, solute particles, which are actually present in the solution divided by number of solute particles taken. Number of solute particles in the solution and number of particles taken may be equal or may not be equal. These will be equal if a solute is non-electrolyte, means it doesn't get associated or dissociated when mixed with water. For example, glucose. Glucose is non-electrolyte. For example, sucrose. It is non-electrolyte. Urea again is non-electrolyte solute. Now, what are the examples of electrolyte solutes? Like NaCl. It gets dissociated when dissolved in water. NaCl will dissociated into Na positive, Cl negative. So if we'll start with 1 mole of NaCl, we'll end up having 2 moles, which will directly affect the value of colligative property. Okay. After this example, now we will establish a mathematical relationship between I and alpha in case of a solute which undergoes dissociation. For general relationship, consider electrolyte An, which dissociates into Na. For example, A2 dissociated into A and A. N molecules of N parts of A join to form An. Initial, let us suppose we are starting with 1 mole of this An. We have 0 moles of Na. Final. It's N alpha, and obviously alpha is the degree of dissociation as explained earlier. How many left? 1 minus alpha. Value of I, remember, I is the number of solute particles in the solution divided by number of solute particles taken. So I is 1 minus alpha plus n alpha. Now you know what is I, you know what is alpha. What is this? N. Students, n is the number of particles formed by the complete dissociation of a solute molecule. For example, NaCl. It dissociated to give Na positive, Cl negative. So what is the value of N? It's 2. Hopefully somewhat is clear to you about N. Back to this. I is number of solute particles inside the solution, that is 1 minus alpha plus n alpha divided by number of solute particles taken. So I minus 1 is equal to minus alpha plus n alpha. I minus 1 is equal to, I am taking alpha common, n minus 1. So alpha is I minus 1 upon n minus 1. This is the mathematical relationship between alpha, degree of dissociation, and want of factor I. Now you can cross verify this with the help of our previous example of that pens. Alpha is, in that example, alpha is equal to, what is the I in that case? Remember, 1.33. Rewind the video to confirm this. 1.33 minus 1 upon 2 minus 1. Why? 2 pen. 1 pen dissociated into 2 particles. So n is the number of particles formed after complete dissociation of one solute particles. 2. Solve for alpha. Alpha is 0.33 upon 1, 0.33. Same as in that example. Students, now I'll proceed with some small numerical problems. First problem is, note down, calculate the value of alpha for an electrolyte of type AB2, which has I equal to 2.24. What is asked? Alpha. Alpha is question mark of electrolyte of type AB2. AB2. This electrolyte of type AB2 dissociates like A plus B plus B. Simple. 1 ion of A plus 2 ions of B. Number of particles are enough for the numerical problem. But if you want to write a complete signs, charges, you can balance A2 positive, B negative, B negative. So what is the value of N here? N is 3. Alpha is asked. N3 from type of salt. I was 2.24, I think. Yes, 2.24. Now, from the formula, alpha is equal to I minus 1 upon N minus 1. I is 2.24 minus 1 upon 3 minus 1. Alpha is 1.24 upon 2.62. Degree of dissociation is 0.62. Percentage dissociation. Percentage dissociation is, students, alpha into 100, which is equal to 0.62 into 100 equal to 62. Okay? Just note it down. Next numerical problem is to calculate I from alpha. I. Alpha for electrolyte is given and value of alpha is 0.54. Type of salt is A2B3. Now from A2B3 we can calculate N. 2 particles of A, 3 particles of B. Signs A3 positive, B2 negative, but we are interested only in number of particles. N is 5. We have N. Also alpha is given. So can we calculate I? Yes. Alpha is I minus 1 upon N minus 1. Put the value of alpha. Alpha is 0.54 is equal to I minus 1 upon 5 minus 1. So it is 0.54 into 4 I minus 1. 16, 20, 21, 2.16 equal to I minus 1. I is equal to 2.16 plus 1, which is 3.16. Okay. Now students, some points to remember. First, and obviously the most important, what is I? Check. I is the ratio of number of solute particles which are actually present in solution after dissociation or association to the number of solute particles taken. Second is alpha. Check. Alpha is the ratio of number of solute particles which actually getting dissociated or associated to the number of solute particles taken. N. N is the number of particles formed by the complete dissociation of one molecule of solute. Okay? For a solute, which undergoes dissociation, what is the value of I? Students, I is always be greater than 1. Very important. I will be greater than 1 for a solute which undergoes dissociation in solution. Okay. In next lecture, I'll discuss about solute, its value of I and alpha, which undergoes association. And also we'll start with colligative properties. Till then, make some numerical problems and try to solve them. Thanks.